Okay, so welcome to 7.4, which is fractals. Okay, so what is a fractal? So definition. So a fractal is an object that displays self-similarity. So a fractal is an object that displays self-similarity. Self-similarity. At infinitely many magnifications. So at infinitely many magnifications. Magnifications. Both inwards and outwards. Okay, so let's recall or learn for the first time, depending. So recall. So the dimension of a point, a point, like just a dot, a single point, is d equals to 0. And that's because you can't move in any direction. Next, the dimension of a line, in which you can move back and forth. The dimension of a line. Dimension of a line. A line. Like so. Is d equals to 1. Now let's go into dimension 2. So that's a plane, like a piece of paper. So the dimension of a plane. So think of a piece of paper. Is d equals to 2, because I have 2 directions I can move in. And finally, the dimension of a solid. The dimension of a solid, like a box, is 3. So it's more now in 3 dimensions. And let's note, fractals are generated using iterations. So fractals are generated using iterations. Let's call it n, given a starting image, n equals to 0. So what do I mean by this? Let me show you with examples. Okay, so the first example is called the Cantor set. So the Cantor set after Georg Cantor. Cantor set. Okay, so for the n equals 0, in the Cantor set, what we're given is a line, any line. So n equals 0, that's a given iteration. We're given just a line, so let me count. So 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 2, 3, 4, Okay, I want my line to be this long. So I'm given a line segment. Okay, so the first iteration of the Cantor set, that's n equals to 1. What I'm going to do is I'm going to create the same line, but now I'm going to omit the middle third. So I take the middle third of it and I cut it. So this is the first iteration of the Cantor set. So now the next iteration, n equals to 2. I take the previous iteration, which is the segment on the left here, and the segment on the right here, and I perform the same action, meaning I take the middle third from each of the remaining line segments. So I just cut the middle third out. Now let's do one more iteration. This goes on infinitely, but actually let me make that not pink. So the third iteration, we'll take the previous iteration, number 2, and each of its line segments, of which there are now 4, I'm going to take the middle third of those guys. No, not drawn perfectly, but you get the idea. And this goes on forever and ever. Okay, so let's note. Let's look at something. Do you agree that the length of this guy here is 1/3 the length of the original? So if there's a way I could draw that better, maybe I'll do it here. So note, at any level of iteration, I don't like the way that sounds. Let me put at any iteration level, that sounds better. At any iteration level, we require a multiplication factor of 3 to return to the previous length. So that is this length here would need to multiply by 3 to get the previous length there. And this is the same all the way through. So let's consider, if I do this forever and ever, I keep on omitting the middle third in the Cantor set. So will the Cantor set arrive at infinitely many points or lines? Infinitely many points or lines? Well, that's a good question, and we'll get to that later. Now let's do another example of a fractal, and that is the Koch triangle. It's usually a snowflake, but I don't want to do the whole snowflake, so I'm just going to do one of the arms of the snowflake. Okay, so the first iteration given is n equals to 0. And that's what's given, right? It's not an iteration, it's just what's given. And in this case, let's go ahead and do 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll do, so this is iteration 0. So now iteration 1, so n equals to 1. I hope I have enough space, let's see. I'll just do a couple iterations. Let me copy. Why won't it let me paste? Okay, what's going on? Copy, paste. There we go. Okay, so now what I want to do, let me move this over here. And let's call it the darker purple. So similarly to the Cantor set, I'm going to remove the middle third. But when I remove that middle third, I'm going to create an equilateral, or two parts of an equilateral triangle. So that's the first iteration. So now the second iteration, what color did I use? I think I used that. So n equals to 2. I'm going to take the previous iteration, which now has 4 distinct lines. And I'm going to omit the middle third of each line segment. And on each of those line segments I omitted, I'm going to create an equilateral triangle, or two parts of an equilateral triangle. No, okay. What is it? Why won't it let me? Okay, clearly it's not going to let me draw this well. Don't know why. Yep, it keeps on auto-correcting. Gotta love computers. I know I certainly don't. Ugh, if I don't, really. Okay, yep. These are our future rulers, our overlords. Okay, where was I? Oh yes, making an equilateral triangle here. Okay, so you can kind of see how this is turning into what looks like a snowflake after just 2 iterations. But now I've got, let's see, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16 line segments. So each of those in the next iteration would have to have an equilateral triangle, or 2 sides of an equilateral triangle put on each of those little line segments. So let's note. What is a magnification factor? So note. Well, if I were to look at this guy here, which has a width of 3 units, and this guy here, which has a width of 9 units, it looks like the magnification factor is also 3 for this one. So there is a magnification factor of 3 to arrive at the previous iteration. Not the previous iteration. So we see that if this goes on forever and ever, amen, that we're going from a line to something that's going to be so complicated it might almost be area. So let's consider. So will the Koch triangle converge? So will the Koch triangle converge to an object with dimension 1 or 2. So 1 is the dimension of a line, and 2 is a dimension of an object with area, like a plane. And once again, we'll come back to that in a bit. So another famous fractal is called the Sierpinski triangle. So for example, the Sierpinski triangle. Okay, so the given object is an equilateral triangle. So let me first try and draw that. It's always the hardest part. It's supposed to autocorrect. I don't think it ever really does. Does that look like an equilateral triangle? Doesn't look like an equilateral triangle to me, but yeah. I'm going to take this and move this down a bit. So this is iteration, this is what's given, n equals to 0. Okay, so now let's copy and paste it. And I'm going to change the color to darker purple. So at iteration 1, what we're going to do is we're going to take and draw a triangle upside down inside here. Nope, okay, I guess we're not going to do that. And we're going to we're going to cut the middle triangle here out. Let me zoom in, try and color this a bit better, quicker. So I'm cutting out the middle triangle. So what I'm left with, you'll notice, is 3 triangles at the corners. So this is iteration 1. I went from 1 triangle to 3. By cutting out the middle triangle. Okay. Almost. Good enough for government work, hopefully. Okay, so that is iteration 1. So let me copy and paste that, because clearly we have 3 triangles here. So iteration 2, what is iteration 2 going to do? Well, it's going to take, oops, let me make this a different color. It's going to take the remaining 3 triangles and omit from them the middle triangle. Does that look like it's straight? Okay, so I omit the middle triangle here. Those white dots are going to drive me crazy. Not that it matters. So at each iteration in the Sierpinski triangle, we omit the middle of each remaining triangle. So we're taking out the triangle in the middle. Okay, I think I did it. Okay, let's see. Okay, so kind of getting the idea. So what is a magnification factor? If I look at this little guy here, which has a length of 3, to go to this guy here, which has a length of 6. So it looks like now my magnification factor is 2. So the magnification factor to arrive back at the previous iteration is 2. So it differs this time. So once again, I want to consider if we're taking away area forever, because the iterations go on infinitely, will I have any area left? So will the Sierpinski triangle have any area remaining? So these are things to think about. We'll get to them, but just think about them for now. Okay, so terminology. And the term fractal refers to the non-integer dimension of fractal objects. So it refers to the non-integer dimensions, of fractal objects. So what do I mean? Well, first let's see a theorem. Non-integer. Okay, so the dimension of a given fractal. So the dimension of a given fractal is given by so we'll call it D. So the dimension D is going to be a quotient. So it's going to be log, which has base 10 because it's not written. And it's going to be log of the number of self-similar replications. So number of self-similar replicas divided by log, which has base 10, of the magnification factor. Okay, so let's do an example. Let's look at the previous guys we've already looked at. So example. So find the dimension. Find the dimensions of the following fractals. And if this writing looks like I'm exhausted, it's because I am. Okay. So number 1, let's do the Cantor set. So let me just go ahead and copy and paste And let's just copy and paste. Well, why don't I do the whole thing? So copy and paste. So this is our Cantor set. Okay, so do you agree that the number of self-similar objects at any step is going to be 2? Because from here, I go from 1 to 2. So 1 to 2. Right, I went from 1 line to 2. And each line goes from 1 to 2. So let me write that formally. I don't like that, the way that looks. One, two, two. Okay, so I have the number of self-similar replicas is equal to 2, right? Because each one line becomes 2 at each step. And the magnification factor we already know. That was 3, right? Because I need to multiply it by 3 times. Okay, so I claim that dimension D is going to be log of the number of self-similar replicas, which is 2, divided by log of the magnification factor, which is 3. So what you're going to do in your calculator, you should have a log 2 button. So what you're going to do LOG. You should have that button, LOG. Then you're going to press 2. And then equals. And then divided by. Then log. And then 3. And then equals. And what I got for that was 0.631. And notice this is between a point, D equals to 0, and a line, D equals to 1. So the Cantor set is between dimensions. It's not quite a point. It's more than a point, but it's less than a line. So that's why it's called a fractal, because the dimension is fraction, non-integer. So let's do the other couple ones. So the next one, number 2, let's do the Sierpinski triangle. I'll just leave it there. Sierpinski triangle. So let me copy and paste that one. Sierpinski, here we are. Copy and paste. Okay, so do you agree that I went from one, two, 3 triangles, going from step 1 to step 2? So each triangle becomes 3 at each iteration. So there's number pardon me, number of self-similar replicas. Of self-similar replicas is equal to 3. And we already found that the magnification factor was equal to 2. So is this the same as a Cantor set? No, it's actually the opposite. So the dimension for the Sierpinski triangle will be log of the number of self-similar replicas, which is 3, divided by log of the magnification factor, which is 2. So hopefully, did I get that right above? Yes, I did. Okay. And what I get when I put that in my calculator is 1.585. So that's between where? Well, between a line, which has dimension equals to 1, and a plain piece of paper, which has dimension equals to 2. So it's not quite planar, so it doesn't quite have area. It's in between the two dimensions, hence fractal. Okay, so I guess we'll go ahead and do the Koch snowflake. Why not? So number 3, the Koch snowflake. Actually, I called it the Koch triangle because I didn't do the whole snowflake, so we'll just do the Koch triangle. Okay, so where was that? Here it is, these 3 guys. Copy. Paste. Okay, so how many self-similar objects do I have, or replicas? Well, I went from one line at the beginning here. One line. 1 to 4, right? One line to 1, 2, 3, 4 lines. So there's actually 4 self-similar replicas or lines. So number of self-similar replicas is equal to 4. And we found that the magnification factor we saw that it went from 3 to 9, so it was 3, right? So the dimension here is going to be log of 4, the number of self-similar replicas, divided by log of 3, the magnification factor. Okay, and that gives me 1.262, which is once again between a line and a plane. So between a line where the dimension is 1 and a plane where the dimension is 2. So notice I'm increasing from dimension 1. I started with a line, but by making the line more and more complicated, if I take this to the infinite iteration, I get something that's almost like a piece of paper. Whereas in the Sierpinski triangle, I began with a piece of paper or a plane, and I kept on taking away from it. So I'm going down in dimension. Okay, so let's see. We've only got one more subtopic for this, and that is Pascal's triangle. So Pascal's triangle. Okay, so we begin Pascal's triangle, number 1. So begin with a triangle of 3 ones. So begin with a triangle of 3 ones. Number 2, we begin and end each subsequent row with a 1. So begin and end each subsequent row with 1. Number 3, so place the entries of each row in between the entries of the row above it. So place the entries of each row. This will make sense once we draw it. The entry of each row. In between the entries of the row above it. And finally, so the values of each row's entry are the sum of the 2 diagonal above it. So the values of each row are the sum of the 2 entries above and diagonal to it. Above and diagonal to it. Diagonal to it. So I think what I'm going to do is move this instructions down because I need a bit more. Well, maybe I could just move these guys down. I hope you don't mind that I'm putting them on different pages. I hope that's not going to be a problem. Let me at least give this a bit more room. Okay, so let's see. What do we have each? And I need to clean this up a bit. Okay, so what should I do? Let's underline this row in dark blue. So I begin with a triangle of 1s. So let's go to the next page. And I'm going to begin with a triangle 1, 1, 1. Okay, so now begin and end each subsequent row with 1. So I'm going to begin the next row with 1 and end the next row with 1. But then I'm going to place the entries of each row in between the entries of the row above it. Okay, got that. That's really telling me where to place it, but it's not telling me what the value is. Well, the value of each row are the sum of the two entries above it. So let me actually put that in yellow. Above and diagonal to it. Oh no, why did those go through? Did I move this down too far? Let's see, maybe now it won't go through them. Okay, so what that means is I'm here in the third row, and I claim that this entry is 2. Why? Because it's in between the two guys above it, and it's the sum of the two entries above it. So let's go ahead and begin the next row with 1, end it with 1, and now I know I'm going to take the sum of the two guys above that. Okay, so what is 1 plus 2? It's 3. And what is 2 plus 1? It's also 3. Okay, so now I begin the next row with 1, and the next row with 1. Do the same thing. What is the sum of 1 and 3? And that's 4. What is the sum of 3 and 3? Oh, that's 6. What is the sum of 3 and 1? Well, that's 4. And we can keep on doing this forever. So 1, end with 1, begin with 1. So we have 4 plus 1 is 5. We have 4 plus 6 is 10. We have 6 plus 4 is also 10. And then we have 4 plus 1 is 5. Okay, let's go on a bit more. So 1 and 1. So 1 plus 5 is 6. It looks like I have these out of order a bit. Put this, maybe a bit there. Maybe a bit there. It seems like this is getting a bit tight. Okay, so 5 and 10 is 15. 10 and 10 is 20. Let me do that in orange. 10 and 5 is 15. 5 and 1 is 6. Okay. So this goes on infinitely, of course. So this is Pascal's triangle. This can go on forever and ever. So Pascal's triangle. But that's how we create the triangle. We start with the trinity of ones and just add the two guys above it forever and ever. Okay, so let's consider Pascal's triangle, but let's get rid or omit. So consider the omission of all even numbers from Pascal's triangle. So I'm going to just go ahead and rewrite Pascal's triangle. Let's see, maybe a little darker, but I'm going to 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, then 21, then 35, 35, 21, 7, and 1. 1, 8, 21 and 7, that's 28. 21 and 35 is 56, then 70, then 56, then 28, then 8, then 1. Okay, so then 1, 9, 36. Let's see, that's going to be, if that were 30, that would be 86, but I'm too shy. So that's 84. So 5 and a 7 is 12. So 126, 126, 84, 36, 9, and 1. Oh boy, how far should I go? 10. Okay, so 1, 10, 45, 36, and 84 is 40 and 80. So that's 120. 126 and 84, that's going to be 210. 126 and 126 is going to be 252. Hopefully, I got that right. Yes, okay. And now it's symmetric, so I know it's going to be 210, 120, 45, 10, and 1. Okay, I think that's enough. So what I'm going to do is I want to omit, what color should I use? Maybe orange. I'm going to omit all the even numbers, but I'm going to do them in a very sneaky way. So I'm going to do this. So I'll get rid of that too. And then look at all these even numbers here. They go to this 20 down here. So I'll omit all these even numbers here. And wait, there's an even number right here that I can omit. Oh, but wait, there's also an even number, the same even number over here that I can omit. Oh, but then there's all these even numbers, which go on quite a ways downwards. So do you see what I have here is the Sierpinski triangle if I go on forever with this. So what's interesting is we've got the fractal, the Sierpinski triangle, within Pascal's triangle. If I were to have gone on a little bit longer, but this is pretty amazing, isn't it? And there's also something really cool. Let me show you. So let's note. If we align, if we align if we align Pascal's triangle, left adjusted, so if we align Pascal's triangle, left adjusted, and take the sum along each diagonal. What do we get? So let's do this again. Start with 1, 1, 1, 1, 2, 1. Do I have enough room there? What should I do? So 1, 3, 3, 1. And 1, 4. What did I use? Pink? I can't remember what color I used. Yes, I used pink. 4, 6. 4, 1. And 1, 5. 10, 10, 5, 1. Then let's see how far I could do this. 1, 1, 1, 6. 15. What color did I use in between there? I used orange. So 20. 15. 1, and let's do one more for good measure, shall we? So 1 and 1 will have 7. Notice the green numbers are counting numbers. 1, 2, 3, 4, 5, 6, 7. Oh shoot, I forgot the 6 here. So this will be a 7 here. Wait, did I get those out of line? It looks like they are out of line. How did that happen? That 1 should have gone over a bit. 1, 2, 1, 2, something like that. Okay, so now I can move my 6 over to be a little bit better in line. So 6, and the 7 will go here. Okay, so where was I? So what do we have? We have 21, 21, and 35. 35, 35. Okay, so what I want to do is I want to take this left adjusted, and I want to look at the sums now across the diagonals like so. So this has just one entry, so the sum is just 1. This has just one entry, so the sum is just 1. This diagonal, however, has 2 entries, and 1 plus 1 is 2. This diagonal has 2 entries, 1 plus 2 is 3. This diagonal has 3 entries, 1 plus 3 plus 1 is 5. This diagonal has 3 entries, 1 plus 4 plus 3 is 8. This diagonal has 4 entries, so 1 plus 5 is 6, plus 6 is 12, plus 1 is 13. And finally, since I don't have much room, is, what do we have here? We have 6 plus 4 plus 10 plus 1, that's 21. So look, this is the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21. So the Fibonacci sequence, i.e., the Fibonacci sequence. Which is kind of cool, because that's another sequence, that's something we've seen before that's hidden within Pascal's triangle. In fact, there is tons of stuff hidden within Pascal's triangle. It's a really cool object. Okay, I will see you guys in chapter 8.